The applications of capacitors could seem endless as they are utilised in almost all of today's technology. Capacitors are used in most electronic circuits, such as TVs, mobile phones, computers, and even in cars. The use of these capacitors can be for timing circuits, voltage control, and protection of electronic equipment. Capacitors can even be used on high voltage systems for power factor correction on transmission lines and sub-transmission lines, as you can see the photo of the capacitor bank for an industrial switchboard here. Capacitors are also commonly used in three-phase and single-phase rectifiers, whereby the capacitor is used in parallel with the output to create a smooth and continuous DC output voltage that is compatible and suitable for electronic equipment, such as mobile phones within the mobile phone chargers and battery chargers. In all these applications, we are required to know the characteristics of each capacitor and be able to predict the voltage, charge, and more importantly, the rate and time taken to charge the capacitor to saturation.
Okay, so we've seen some applications of capacitors, but how can we solve engineering problems with them? Well, what we need to know is their charge as a function of time, and we can find this. Most of the mathematics is arbitrary, except for the part which requires the solving of differential equations.
A differential equation is any equation which contains derivatives, either ordinary derivatives or partial derivatives. Variable separable is just a way of solving these differential equations. For example, dy of dx minus 8xy equals 3y. You can move the 8xy to the right, so then the y can be factorized outside, leaving y outside of 3 plus 8x. Here, the values can now be separated, so the y is grouped with the dy, and the x's are grouped with the dx. In doing so, you can then integrate both sides, leaving ln equal to 3x plus 4x squared plus a constant, after it's been simplified. Variable separable differential equations are one of the easiest way of answering differential equations if they can be separable, meaning the x and y's can be split up.
Okay, so now that we have some idea about differential equations, we can derive some equations about capacitors. Let's consider a basic RC circuit with a switch. When the switch is in position 1, it'll be charging. Now we can consider KVL of a series circuit. From here we can divide everything by R. Take note that the current is the flow of charge. If we multiply the first term by C over C, it's the same as multiplying by 1. Now we can replace CV with Q0. Rearranging gives us this. This is clearly the form of a variable separable differential equation. So we can solve this. We'll separate the terms and then we'll integrate the left from 0 to some charge Q, and we'll integrate the right from 0 to some time t. From here we can apply the boundary conditions and we end up with this equation. Well, how does this help us? We've just gone from one equation to another. If you have a good look at this equation, this is exactly what we wanted. We've got a function of charge dependent on time. Notice all the variables in this equation are variables we can control. Consider this circuit. This circuit is clearly dependent on the discharge time of the capacitor. So if we know how long we want the capacitor to be discharging, we can change one of the other variables to get the value we want.
Okay, let's recap. What have we learned? We've seen various applications of capacitors in real-life scenarios, such as rectifiers, motor control, power factor correction, and also timing circuits. We've also learned how to solve a variable separable differential equation and also apply the calculations to real-life scenarios, being the charging phase of a capacitor and the timing circuit. And that's it for today's presentation on the applications of differential equations.